First of all, thank you so much for inviting me and giving me the opportunity to present my research. I really appreciate it. Today, I'm going to talk about incorporating survival data to case control studies with incident and prevalent cases. This is a joint work with Dr. Jing Qin at the National Institute of Allergy and Infectious Diseases and my mentor, Dr. Ruth Pfeiffer at the National Cancer Institute. So here's an outline of today's talk. I will start with a brief introduction to case control studies. And then I'm going to talk about a recent work where prevalent cases were introduced to case control studies. And then I will talk about our work where we introduce prospective survival information to case control studies that include prevalent cases. And finally, I'm going to show you some results based on simulations as well as the United States Radiologic Technologists study. So let's start with a brief introduction to case control studies. The aim here is to study the association of disease incidence with exposure. So ideally, you will start with a cohort of exposed and non-exposed subjects. You will follow them up and see how many in each group develop the disease. But that is not always feasible because of time constraint and cost constraints. And it is particularly difficult for rare disease scenarios. So what we do in rare disease setup is called retrospective sampling. That means subjects are sampled into the study based on their disease status. So let's say we conduct a study between T star and T star plus delta. Delta is a very short interval of time, so you can think of this as a cross-sectional study. And we sample subjects based on their disease status. So D equal to 0 means the subject is disease-free up to the end of the study, and we call them controls. And D equals to 1 means the subject was diagnosed with disease before the end of study. We call them cases. And once we have sampled them, we look back in time, that is retrospective, and we collect information on the exposure status. So whether they were exposed to specific predictors or not. Now, I'm going to further classify cases into incident cases and prevalent cases. So incident cases are subjects who were diagnosed during the study. So in between T star and T star plus delta. And prevalent cases are subjects who were diagnosed before the study. So they had to survive till T star to be included in the study. Now, case control studies for disease exposure association typically use only incident cases. But if we have prevalent cases available, then we want to use them. And this is especially helpful for rare diseases when we may not have enough, when the disease incidence may be rare. So if prevalent cases are available, we want to use them. Now, including prevalent cases comes with two major challenges. One is called the length bias. So prevalent cases who died before the study are not available for sampling. That means they are left truncated. So if a prevalent case was diagnosed here before T star and they died before T star, then they are not available for sampling during the study, right? So we only observe those with longer survival times. This is called length bias. And then we have biased exposure distribution. If the exposure of interest is associated with survival, then the exposure distribution in prevalent cases will also be biased. So these are the two challenges of using prevalent cases. Now, before I go any further, I want to introduce the concept of backward time, which is very important. So backward time is defined as the length of time between disease diagnosis and the beginning of the study period. So this length of time is called backward time, which we represent by A. Now, notice that for a prevalent case to be observed, they had to survive till T star. That means for observed prevalent cases, the survival time has to be greater than the backward time. If the survival time is smaller than the backward time, that means the prevalent case died before the study and they were not observed. Okay? So this is the idea of backward time. Now, a recent work. So before 2019, there was no method including prevalent cases to case control studies. Maziers, who was a former postdoc at NCI, she worked with Liu, Qin, and Pfeiffer, and they proposed a fully efficient method to estimate log odds ratio of disease exposure association when prevalent cases are included in cross-sectionally sampled case control studies. Now, in cross-sectionally sampled prevalent cases, only the backward times are observed. So you need a fully parametric model for the survival distribution for identifiability purposes. So when I joined NCI, a natural extension of this work was to relax the parametric model assumptions. So our goal is to use prospective survival information to do that. Now, prospective survival information is often available. Case control studies that are sampled from a well-defined cohort can be linked to the US National Death Index, electronic medical records, health insurance claims, SEER Medicare database, etc., to get the prospective information. So how long did the subject survive after disease diagnosis? That information is often available. And our goal is to utilize this information to relax the parametric assumption and hopefully get more efficient estimates for disease exposure association. So I'll start the methodology with a model for cross-sectional case control study. So let D equals to 1 denote a diseased subject, that is a case, and D equal to 0 is disease free, so that's a control. And this is our prospective logistic model. Note that this is a prospective model, meaning that the exposure status is known. So given the exposure status, what is the probability of disease, right? And we are interested in this beta parameter, which is the prospective parameter. So here I'm talking about a prospective logistic model, and I started by discussing a retrospective sampling design, right? So how do we estimate beta retrospectively? That is using the distribution of exposure given disease, the retrospective way. So I'm going to show that next. So define pi as the probability of d equals to 1, and f0x is the exposure distribution for controls. For incident cases, Qin 1998, they used a Bayes theorem to write the exposure distribution for incident cases in terms of the exposure distribution for controls. So you can see this is the retrospective density, and this is the using Bayes theorem to write that in terms of the prospective logistic model. And then we have some adjustment terms. So after some algebraic calculations, we can write this in terms of the exposure distribution for controls. And the remaining term is an exponential term, which is why this is called exponential tilting for incident cases. So you can basically tilt the exposure distribution for controls to get the exposure distribution for incident cases. And so this is for incident cases. Now let's look at prevalent cases. For prevalent cases, we are interested in the joint distribution of the exposure x and the backward time a. So let's say t is the time from disease diagnosis to death, that is our survival time. And the backward time, as I defined before, was the time from disease diagnosis to beginning of the study. We are interested in the joint distribution of x and a given that d equals to 1, which means that which denotes a case, and then t greater than a, which means that the survival time is greater than the backward time. And as I said, that for observed prevalent cases, the survival time has to be greater than the backward time, because if t is less than a, that means the prevalent case died before the beginning of the study, so they were not observed. So for observed prevalent cases, you need these two. So we can split this joint distribution into the conditional distribution of a given x and the exposure distribution given the rest of the terms. So let's focus on the first one, the conditional distribution of a given x. If disease incidence is stationary, then the backward time follows a uniform distribution, 0 tau. And using the fact that a is independent of x and t, Mazières wrote the conditional density in terms as a ratio of the survival function s and mu, which takes care of the left truncation in prevalent cases. So this mu is the probability of t greater than a. And s is your survival function or the survival distribution for the time from disease diagnosis to death. Then we come to the distribution, the exposure distribution for prevalent cases. So for cross-sectional case control studies that include prevalent cases, F2X denotes the exposure distribution for prevalent cases. And Mazières used Bayes theorem again, as well as the backward time follows uniform distribution to write this F2X in terms of the exposure distribution for controls, F0X. And again, you see we have the remaining term is an exponential term, which is why this is again an exponential tilting term. However, this is a different exponential tilting term compared to the incident cases. So now I can write all three of these things. So let's go back a little bit. First, I showed you the exponential tilting for incident cases. Then we looked at these two terms. One was the ratio of S over mu, and the other exponential tilting term for the prevalent cases. And I'm writing all three of these together as the likelihood for incident and prevalent cases in the case control data. So we have F0x for everybody for controls, incident and prevalent cases. For only incident cases, we have the exponential term. For the prevalent cases, we have the exponential tilting term and the ratio of S over mu. And Maziers obtained profile likelihood estimating F0 here non-parametrically by putting mass points on the observed x-axis. And to ensure that the estimated density, so the estimated F0 is a density, we need to impose constraints and use Lagrange multiplier. I'm not going to go into the details of these constraints, but just to give an idea of how F0 is out of this likelihood. So once F0 is profiled out of the likelihood, this is what we are left with. We have the profile log likelihood with the remaining parameters alpha, beta, nu, and zeta. But our main interest is in the beta parameter. And Maziers assumed a fully parametric model for S, which is what we are trying to relax. So now let's look at the new information that we have, which is the prospective follow-up times are now available. So for both incident and prevalent cases, we observe the time from disease diagnosis to death or censoring. Delta denotes the right censoring indicator. So 0 means right censored, 1 otherwise. For incident cases, we observe the minimum of the survival time and the censoring time. So let's say this is the survival time for the incident case. This time can be censored. So we observe the minimum of T and the censoring time C1. For prevalent cases, we have the backward time A and the forward time from end of study to either death or censoring. This forward time can be censored. So we have the backward time plus the minimum of V and C2. And the total survival time is this. So now we can write down the survival likelihood from the survival time for incident cases and the left truncated survival time for prevalent cases. So for incident cases, we have the standard F to the power delta, S to the power 1 minus delta. And for prevalent cases, we need to take care of the left truncation, which is done by mu, which is the probability of T greater than A. And so this is our, this is the term for prevalent cases. So together we have the survival likelihood. And now we combine the survival likelihood with the case control likelihood from before. So we had the profile log likelihood from the case control model. And now we have the log likelihood from the survival model. And one can assume parametric model for the survival function S and maximize the combined log likelihood to get the estimates. However, for semi-parametric survival model, this maximization is impossible. And what I mean by impossible is that it is computationally very, very difficult. However, theoretically, it is still identifiable. So for semi-parametric survival model, we propose a two-step estimation method. In step 1, we model the survival function using semi-parametric Cox model and estimate the parameters. In step 2, we fix the parameters from step 1 and maximize the profile log likelihood LP to estimate the remaining parameters alpha, nu, and beta. So this will be our step 1. We will estimate zeta and then fix the value of zeta to get the estimates for alpha, nu, and beta. And our main interest is in beta. So let's go into the details of each step. So in step 1, we estimate the survival model parameters. Here is the semi-parametric Cox model with lambda 0 as the baseline hazard function. So we want to estimate this lambda 0 and we want to estimate this gamma parameter. And to do that, we extend the EM algorithm by Qin et al. 2011 for censored and truncated data from incident and prevalent cases. Now, I will not go into the details of the EM algorithm, but I want to give you the brief idea of the EM algorithm. So we associate EM algorithm with missing data. So what is our missing information here? For the ith prevalent case that is observed, we assume that MI cases were unobserved or left truncated. So let's say a prevalent case was diagnosed here before the study, and they died also before the study. So these cases constitute our missing data. So for these missing prevalent cases, the data that we are missing is basically the survival time, T dagger, from disease diagnosis to death, and the backward time, which is A dagger from diagnosis to the beginning of the And for these missing prevalent cases, the T dagger is less than A dagger, right? We talked about this before, that survival time less than backward time for missing cases. So this is the idea of the EM algorithm. And once we use this EM algorithm to get the estimates of gamma hat and lambda naught hat. In step 2, we use the gamma hat and lambda naught hat that we got from step 1 to calculate the estimates for the survival distribution and the mu hat. And then we fix their values in the profile log likelihood for the case control data. So so this is the same profile likelihood that I showed you before. However, now these, the zeta parameters, the S hat and mu hat, this has now been fixed at the estimated values. And now we solve for the rest of the parameters, alpha, nu, and beta. And our interest is in the beta parameter. Okay. And I will spend only one slide on asymptotic properties without going into the details of them. So we prove consistency of the Cox model parameters, zeta hat, and we show that when the baseline hazard is estimated non-parametrically, the estimates alpha hat, mu hat, beta hat are consistent and asymptotically normally distributed. Okay, just wanted to mention the asymptotic properties. And now we will go into the simulation setup. How do we generate retrospective data in this, for problem. So for controls, we generate the exposures from a normal distribution with mean 0 and variance covariance matrix sigma with variance 1 and the covariance 0.5. For incident cases, we use importance sampling to generate the exposure from the tilted model. So as you remember from previous slides, the exponential tilting model for incident cases. So we use importance sampling to generate exposures. Here. The survival time t comes from an exponential distribution with lambda e to the power x1 prime beta. We have the censoring distribution, which is uniform, and this eta 1 parameter controls the censoring percentage. And we have the observed survival time, which is the minimum of t and the censoring time C1, right? So this is what we finally observe, the minimum of t and C1. For prevalent cases, we generate the exposure distribution from F1, here, F1, same as for incident cases. And then we generate survival time t from exponential distribution with lambda e to the power x2 prime beta, the backward time a from uniform 0 and tau equals 30. And we select those cases with t greater than a. So we only observe prevalent cases when survival time is greater than backward time. So we only select those subjects with t greater than a. And once we do this selection, it ensures that x2 is now tilted according to its correct tilting distribution, correct tilting model, f2 equals f0 times the exponential tilting term. Of course, this is just one way of generating the data. One can also generate directly from F2. So X2 can be generated directly from F2 using importance sampling and the appropriate weights. Now, censoring time, again, coming from uniform distribution with 0 eta 2. And we observe for prevalent cases, the survival time, which is backward time A plus the minimum of the forward time and the censoring time. So this is how we generate data in the retrospective setting. Now let's look at some simulation results. I'm showing you results for our method, which is the EM, so two-step method with prospective follow-up time, and the Mazier's method, which makes the parametric assumption, which is for their case was a Weibull distribution with shape and scale parameters kappa 1 and kappa 2. For these results, we have 500 replications, and we use 500 controls, 500 incident cases, and 500 prevalent cases. And this table is for 10% censoring. Okay. So the Weibull assumption, the parametric assumption, was only for the Mazier's method. So we have kappa 1, kappa 2 only for them. We do not have this. We estimate the log hazards ratio parameters, the gamma 1 and gamma 2, along with the baseline hazards, which I cannot show you in this table. So let's look at the estimates first. So we have the true value of gamma 1 was 1, and true value of gamma 2 was -1. And as you can see, both methods estimate very well. They both return very similar estimates, and they're both unbiased. And if you look at the standard deviations, our two-step method is more efficient than the Mazier's method. So this was the step 1 estimates. And in step 2, which is our primary interest, the log odds ratio, beta 1 and beta 2, the true values were 1 and -1 again. And the estimates are again spot on. They are, so both methods give us the same estimates. And this is very good because we do not make the parametric assumption that Mazier's makes. And the standard deviations are also exactly same for both methods. Okay, so this is for 10% censoring. So what happens if I now increase the censoring percentage to 50%? Okay, let's look at the step 1 parameters again first. As you can see, the estimates are very good. They are unbiased. And we are still more efficient than the Mazier's method by looking at the standard deviations here. And when we look at the log odds ratios, beta 1 and beta 2, the estimates start to show a little bit of bias, 3% bias here and 4% here. And this is not surprising because when you increase the censoring percentage, what happens is you're losing out information towards the tail of the survival distribution. So without making parametric assumption, it is difficult to estimate the survival distribution, right? So saying parametrically, it's more difficult. So we start to see a little bit of bias creeping into our estimates. Now let's consider one scenario where we increase the censoring percentage to 90% censoring, extremely large censoring setup. And in this case, you will see bias in the log hazards parameters and the log odds parameters. And again, this is not surprising at all because 90% censoring is a very extreme case, which means if you have 500 cases, 450 of them have been censored and only 50 you have observed till death. So this is, and the only reason we study this scenario is because the real data that I'm going to discuss next also has censoring that is approximately 90%. So I just wanted to show you the results from here. Now, how do we correct this bias? Now, okay, I have increased the prevalent cases, the number of prevalent cases from 500 to 1,000. And as you can see, the bias is going down, which is very comforting because, so what we did is we increased the number of prevalent cases, meaning that we now have more information to estimate the survival distribution. So naturally we see a decrease in bias, which is very good. You can, I mean, we also did simulations by increasing the number of incident cases, and we still see improvement in terms of bias. However, I wanted to show you the more realistic setup of adding more prevalent cases, because in real scenarios, you may not be able to go out and get more incident cases, but you may be able to go and get data on more prevalent cases. So this is a more realistic scenario, and we see that the bias is going down. Okay, now I'm going to get to the real data example, which is the United States Radiologic Technologists study. So 146,000 radiologic technologists were enrolled to study the health effects from low dose occupational radiation exposure. And several surveys were conducted between 1984 and 2014, and they collected information on participants' characteristics, exposure, prior health outcome, etc. Blood sample collection was for the genetic analysis began in 1999. The breast cancer case control study used information from the first two surveys, the first one in between 1984 and 89, and the second one in between 1993 and 1998. So this is the part that we are going to focus on, the breast cancer case control study. So let's look at the details of the USRTS breast cancer study. So the goal was to study the association of SNPs in candidate genes with the risk of breast cancer. We define incident cases as women who answered both surveys and were diagnosed with breast cancer between the two surveys. We define prevalent cases as women who answered only one survey and reported a prior breast cancer diagnosis. We define backward time as the difference between year of diagnosis and the year of survey. So finally, we have 711 controls, 386 incident cases, and 227 prevalent cases. And the follow-up information was collected by regular linkage with the National Death Index. And we observed 49 breast cancer deaths during the follow-up, which corresponds to approximately 92% censoring. So what are the covariates used in our risk, the relative risk model for survival distribution? So we have the genotype for this particular SNP, which is coded as a 0-1 variable. We have the age at selection for controls and age at breast cancer diagnosis for cases. This was coded into 5 categories: less than equal to 22 years old, in between 22 and 40, and so on. We have a year when the woman started working as radiation technologist, also coded as 01, depending on whether they started working prior to 1955 or after. We have history of heart disease, which was a yes or no response. And for the logistic model, we have the following covariates. So we have three SNPs, and all of them are coded as 01 variables. We have the age at selection or breast cancer diagnosis that I have already discussed. We have year first work and family history of breast cancer, yes or no response. We have BMI in 20s, so whether the BMI was less than equal to 20, in between 20 to 25, or over 25. And these BMI numbers are collected in the 20s, meaning in between age 20 and 29. We have age BMI interaction, which is the BMI in 20s for those selected or diagnosed after 50 years old, or 0 otherwise. And alcohol consumption level, which was coded as 01 based on whether the subject had greater than or equal to 7 drinks per week. So here's the log hazard ratio estimates. These are the step 1 estimates from our method, the EM, and the Mazier's method. And in the parentheses, we have the standard deviations calculated based on 500 bootstrap samples. And as you can see, the highlighted numbers are the significant variables. So age at diagnosis was found to be significant by both methods. However, your first work was found to be significant only by the Mazier's method. Okay, now these are the step 1 estimates. These are not our primary interest. Our primary interest is in the log odds ratio, the beta estimates, right? So we have the estimates from our EM method and the Mazier's method, and both methods, as you can see, identify the same variables as significant. We have this particular SNP, which is significant. We have the family history of breast cancer and the BMI in 20s as the 3 significant factors in our analysis. So both methods identified the same variables. Mazier's did it using parametric assumptions. We did it without making the parametric assumptions and using prospective survival information. So the same parametric method identifies the same significant variables. So in summary, we incorporated prospective survival information on incident and prevalent cases into the analysis of case control studies with prevalent cases. We have relaxed parametric assumptions for inference in the logistic model. We developed computationally simple two-step method for estimating the disease exposure association, assuming a Cox model for the survival time distribution. And our method of moment type estimate using prospective information are as efficient as the full profile likelihood method of Mazier's using cross-sectional data. So what we lose by using a method of moment type estimate, we gain back using the prospective survival information. Some future work. So here we are considering right-censored follow-up times. So this can be generalized to interval-censored follow-up times. Our method can be extended to incorporate longitudinal covariates. And we can also consider more general models for the hazard function. So instead of the Cox model, the Cox proportional hazards model, we can use a more general semi-parametric transformation model, which includes the popular Cox model and the proportional odds model as special cases. So here are some of the references. And thank you for your attention.
Thank you very much, Soutrik. Any questions for Soutrik? If you want to ask a question, make sure you unmute your mic and then you can speak. Okay, well, while we're waiting, I have a clarification question for you. You have year first worked and you have defined it as before or after 1955. What is the significance of 1955?
So this was from the questionnaire. So this wasn't something that we defined, it's how the data was collected. So when the data was collected based on the surveys, they asked whether the radiation technology started working before or after 1955.
So I assume something changed in the technology at that time. Maybe that's what that was. Okay.
Maybe newer technologies made radiation, the impact of radiation much lower, something like that.
Mm-hmm. Okay. Okay. Thank you. Any other questions for Soutrik? All right. Well, thank you, Soutrik. That was a very good talk.
Thank you so much.
We appreciate it. Thank you.